Hello, everyone. Welcome to Stat 310, Lecture 21. This is going to be the penultimate lecture on new content. So there's going to be Lecture 21 and then Lecture 22, and that'll be it in terms of our new content. And we're going to cover kind of the last key topic in the course, which will be in Chapter 14, which is simple linear regression. So in the previous couple of lectures, we covered ANOVA, which was in chapter 12, and that was kind of a way of dealing with the scenario where you have responses Yij, where kind of I is a sample index, but J potentially or I potentially indicates that you're in a different group. So it might indicate which state you're in. If you have binary groups like maybe gender, if you believe in gender in binary genders, then you could think about kind of dividing the groups that way, or more groups of gender, and so let me just write that more clearly. So the and so that was what the focus of ANOVA was. But in many settings, and we're going to learn probably one of the most widely used tools in statistics here, you kind of have continuous covariate information. So in some sense, you can't really divide your Ys or your responses into kind of categories or groups in a natural way. Rather, they kind of sit on some continuum. So to give you two concrete examples, imagine a scenario where you're looking at people's weights, but then you also have information about their heights, right? So you could certainly imagine, like, height is generally measured as a continuous variable, and then you want to model the weight of individuals, and you certainly expect it to be very related to the height, but one thing you could do if you wanted to apply ANOVA would be to maybe break into different categories, like maybe 5 to 6 feet, 4 to 5 feet, and so on. But this is kind of suboptimal because you're losing some information about what the height actually is. Another example would be SAT. If you had information about someone's SAT and you wanted to predict their university GPA, clearly you could, if you wanted to do an ANOVA analysis, you could kind of break the SAT scores down into maybe, whatever, the top 10% and then the next 10% and so on. But this is, again, not ideally what you want to use. If you could somehow use the continuous information within X, then that would kind of be, if you have a methodology to deal with that, that would be kind of the best way to model the GPA or weight when you have this extra information. So we'd ideally like to treat these xi's as continuous, and this is the purpose of linear regression. So you can think about this as being like the extension of ANOVA to case with continuous rather than categorical covariate information. So obviously we had categorical covariate information when we're dealing with ANOVA. You might know what state someone's from, and that's kind of a category. But on the other hand, for examples here that we see, like SAT and height, your covariate information is continuous, and you kind of want to use that continuous value to in some ways, and that's what simple linear regression does. And so to be clear, we in case p equals 1, so that what that means is that there's one covariate. So in the textbook, they start with kind of the general x1 through to xp, where you might have various different covariates. Like you might have if you're looking to model weight, you might have like height as one feature. You might have like country or gender as another feature. And you could certainly model that using linear regression as well. And so here we're just focusing on the case where p equals 1, where you only have one covariate, and that's all that will be kind of covered and tested. Certainly, extending beyond p equals 1, a lot of the ideas are very similar, but the math gets a little bit more involved. So we're going to focus on the case where p equals 1. So just to kind of to go back again to the statistical framework. So this is where we're going to talk about simple linear regression, and so by the end of these couple of lectures, we're going to be able to understand simple linear regression in the context of the statistical framework. So one thing that we have here again is the data. So here we've got xi, yi, I equals 1 to n. So n is the sample size. And we're saying that xi here is like is the covariate, and yi is the response to be modeled. So this language of covariate and response, you can also think about it as, you can think about this as the independent variable. And y is the dependent variable. So there are various different terms used for these because regression is such a widely used tool. And so I'm just giving you a couple. So I'll often refer to them as covariate and response for x and y. But they're also sometimes referred to as the independent and the dependent variable. And so this is sort of important lingo to be familiar with when you're talking about regression, because it's so widely used, and it kind of is referred to in different ways in different fields. So that's our data. So, we could think about here, as I've already mentioned. Example, we could have like xi is like the SAT score that someone has, and y is the GPA. So the second thing is the model, or the statistical model. So this is where it's a linear relationship. So what that means is that we have that y is going to be equal to beta 0 is like an intercept or a mean term. We'll talk about some interpretations for that shortly. Then beta 1 is kind of the coefficient that relates the x's to the y's, and it's called linear because I'll use the term linear model here. And then you have some error term here, and we typically model this as we have in the last couple of chapters as normal 0 sigma squared, and again these are independent. So the epsilon i's here clearly are going to be seen as independent. Okay, and so that's kind of the starting point, and why it's called linear regression is we're trying to kind of fit a line to our data. And so so I guess one thing I should mention first is so in this model, so there's 3 parameters of interest. There's beta 0, which is like the intercept term. And I'll give some intuition behind that. Beta 1 is like the gradient or slope of the line. And then sigma squared is the variance, or so how noisy is data around the line. So the main focus of today, main focus for today's lecture is so we're finding good estimates. Estimators for beta 0, beta 1, and sigma squared. We're going to focus more on beta 0 and beta 1 because they're typically of greater interest. But sigma squared is also important because that's going to come in later when we start to talk about like confidence intervals and hypothesis tests. Okay, so just to give a so just to give a geometric picture, and you can kind of have your favorite example going on in the back of your mind, like whether it's SAT, GPA, height, weight, or any other example you might think of about relating two variables that and what they look at. So your data here is of the form xi, y. So every data point here is really a pair. So you can imagine that you have your x here and your y, and then you have a whole bunch of points. And I'm just kind of sort of putting them somewhere here like this. So this is what your data might look at like. So here, n is this is what your data might look like. And then you want to say, like the broad question that you're trying to ask is to find a line that best fits this data. Okay, and so, there's many different choices you could have. You could maybe say, well, let's pick a line that maybe, looks like this, maybe a line that looks like this is better. And so we want to, so the idea is that beta 0, beta 1 determine best, or I should say, so we choose beta 0 and beta 1 to be best linear fit of the data. So obviously, we can, fit the data however we want, and we can choose any line, but somehow we want the line to be the best. And so if we just look at our data and think about it, what does best mean? And so, like the idea here is, so I'm going to draw another one so that we can kind of see maybe fewer data points and what it might look like. What we want to do is we can choose any line that we like through beta 0 and beta 1. So beta 0 is like, so we can say maybe that, this is beta 0 is like that's correct. So beta 0 is like the intercept term here. And then, beta 1 is like the gradient. What we want to do is to choose a beta 0 that, in some sense, we want to choose beta 0 and beta 1 that minimizes distance between line and n data points. So like the best one is the one that gives it. So the best line is the line that gives minimum distance. And the notion of distance that we use here is kind of is the Euclidean distance, which is, and that this leads to the least squares estimator. This leads to the least squares estimator. So what that is that you have beta hat 0, beta hat 1. That's going to, we're used to kind of minimizing or maximizing objectives when we talked about maximum likelihood, and we're going to do that here as well. So that is just yi, it's the best fit. So, and we square it because we're talking about Euclidean distance. So we're adding up all of the, so what this is so, yi minus beta 0 minus beta 1 xi squared. That's the Euclidean distance between yi and beta 0 plus beta 1 xi. So that's essentially what we're doing. We're going to choose the beta 0 and beta 1 such as this distance is as small as possible. Okay, and so finding beta 0 and beta 1. So we have this objective that we want to minimize. So how do we do that? So we do what we always do here, which is to differentiate and set the derivative to 0. So if we let I'll call this the we'll call this maybe the residuals, beta 0 of beta 1. So you're going to call this whole objective like the residuals. Which is a function of beta 0 and beta 1. We're calling it residuals just because it, let me just shorten the notation here and just say this is R of beta 0, because it's kind of what's like the residual of what's left over. And so, if we want to differentiate, so we can take the derivative of this with respect to beta 0, and we want to set that to 0, and then we want to take the residual this with respect to beta 1 and set that to 0, and then hopefully, and then that is going to give us give us our solution to beta hat 0 and beta hat 1. Okay, and so let's take the derivatives now. So so that's going to be equal to, if we take the derivative with respect to beta 0, you're just going to get, and you're going to get 2 times, because there's nothing in front of the beta 0, this is just, okay, and then instead in here, where because there's an xi in front of the beta 1, you're going to get an xi here. Okay, and so what we need, if we want the derivative to be 0, we have that we can drop the 2 because it doesn't really matter when we're adding up things to be 0. You have so we have these 2 equations, and this is perfect because we have 2 equations and 2 unknowns that we need to solve for. So that that equals to 0. So So we're going to let x bar equal to 1 over n, and then y bar is 1 over n, the sum of the y's. Okay, and so now let's try to solve for this. So if we call this equation 1 and equation 2, then 1 is going to become beta hat 0 plus, that just equals y bar. So we have that beta hat 0 equals y bar minus beta hat 1 x bar. And what this does intuitively, it ensures that the regression line goes through the point x bar y bar. So it goes to the point where they're both even. And you can check that if you plug this back in, this guarantees that the regression line always goes through the point x bar y bar. And then the question is, what's the gradient? And so we kind of get that by solving the second equation. So we have that. So we have so let me just so to solve this second equation, we have so we have this equals to 0. And then we also know that beta hat 0 from the first equation equals to y bar minus beta hat 1 x bar, and that's from 1. Okay, and so that means that we can plug that in and we will get an equation just in terms of beta hat 1 when we do that. So we get so that is equal to 0. And so when we rearrange, that means that we have beta hat 1 and then so this thing is going to equal to, okay, and so you can clearly see that then that beta hat 1 is just going to be okay, so we're gonna just talk a little bit about this because potentially if you've seeing this for the first time, it looks a little bit slightly kind of unintuitive. So we're gonna talk a little bit about this shortly. So we have that this is beta hat 1, and then we also have that beta hat 0 equals, like once you know beta hat 1, beta hat 0 equals y bar minus beta hat 1 x bar. Okay, so what we're gonna do is, for now, these are just kind of expressions that we don't really know a lot about and aren't super intuitive. But our idea is we're going to kind of try to give some intuition about this, and then also and then also kind of think about ways that we can calculate these quantities efficiently. So this is, so beta hat 1 here is the slope. And we'll later see that, we'll see that it is related to correlation. Okay, so let's first discuss some properties. So the first thing to note is, so note that we have that E of beta hat 0 is equal to beta 0, and E of beta hat 1 is equal to beta 1. So how do we show that? So this is just a reasonable sanity check that our estimates are unbiased and at least doing something sensible. To show this, we know that yi is equal to y is equal to beta 0 plus beta 1 xi plus epsilon I. And then obviously y bar is equal to beta 0 plus beta 1 x bar. And then plus epsilon bar. Epsilon bar here is just 1 over n. It's just this average. And so when we, if you look at that, therefore we can say that expectation of yi here is just beta 0 plus beta 1 xi. And then expectation of y bar is equal to beta 0 plus beta 1 x bar. So now let's plug that in. So if we look at beta hat 0, if we look at the expectation of beta hat 0, that's going to be equal to the expectation of y bar minus the expectation of beta hat 1 times x bar. And so that's just going to be equal to beta 0 plus beta 1 x bar, and then minus expectation of beta hat 1 x bar. We have that this is beta 0 plus x bar times beta 1 minus expectation of beta hat 1. So it just remains to show that expectation of beta hat 1 is what we expect. So let's look at expectation of beta hat 1 is equal to, so remember here, and this is the important thing to keep in mind, is that the xi's are all treated as fixed numbers, whereas the yi's are treated as random. So you need to take expectations with the yi's, not with the xi's. And the denominator, we can just kind of leave it as it is because it does not have any y's in it, so there's no randomness in the denominator. And so this is equal to yi minus y bar and so we get that expectation of y minus y bar equals to, according to what we have, it's just going to be expectation of yi minus expectation of y bar. And so that's going to be beta 0 plus beta 1 xi minus beta 0 minus beta 1 x bar. And so that's all just going to be equal to beta 1 times xi minus x bar. And so when you plug that in, this is just equal to xi times beta 1 xi times xi minus x bar. And so you can clearly see after rearranging that this whole thing is just equal to beta 1. So we have that, the expectation of beta hat 1 equals beta 1, and that the expectation of beta hat 0 equals beta 0. Okay, so this is a reasonable kind of sanity check to begin with. Okay, and so that's kind of a first sanity check. Another thing is calculating or interpreting beta 0 and beta 1. So we have that and beta hat 1 here is the sum So another thing that's worth noting is that another way to write this out. So it's equivalent to so this might look a little bit weird as to why that's true. To convince yourself of why that's true, note that this is true since the summation I equals 1 to n, like x bar times yi minus y bar is equal to 0, because if you add up things and then subtract off the mean, that should be 0. And also obviously we have that the same thing is true for the x's, that if you add up the x bar, that equals 0. So all I've done is just added these two terms in both the numerator and the denominator, and they're both 0. So that's why we can, or we've subtracted these terms in the numerator and the denominator. So I'll just write that out explicitly just so there's no confusion. So from our original expression, we have that okay, and then we can certainly say that this is just the same thing as adding and subtracting 0, and that's just minus So all I've done here is just added and subtracted 0 to the numerator and the denominator, and that gives you exactly the expressions that we have here. Okay, so why is this actually useful? Because this means that beta hat 1 is actually connected to a couple of the key sort of statistics that we have here. So we have here that we're going to define like sx squared, which is just 1 over n xi minus x bar squared. I haven't bothered doing any correction here because of the fact that the x's here are not random variables, so I'm just going to normalize by 1 over n, and so this is one data dependent quantity. And the other thing we have is that rho hat squared here it's like a this is a sample correlation coefficient. A sample correlation coefficient squared. Okay, and so what that means is that so the beta hat 1 here is just the sample correlation coefficient squared divided by the variance of x, or the standard deviation of x squared. And then we have that beta hat 0 is equal to y bar minus beta hat 1 times x bar. Okay, and so this gives an interpretation that therefore beta hat 1 is just that is incorrect, I believe. It should just be there shouldn't be a squared here. That's my bad here. That's just the definition. I'm sorry. There shouldn't be a squared there. So beta hat 1 is really just a measure of the correlation normalized by Sx squared, because you need to normalize by the variables. So no, so that's actually incorrect too. Let me just be a little bit clearer here. So this is what the actual sample correlation should be. So I'm sorry about this. Yeah, if we wanted to actually to say what the sample correlation is, it's going to be okay. So this is what the actual sample correlation is, and okay, and so therefore beta hat 1 is just equal to rho hat times sy over sx. So sy here is equal to 1 over n yi minus y bar squared. So this is what our regression coefficient looks like. It's just going to be the rho hat and then normalized by sy and sx. So we have that this is what sy squared looks like. And to understand the interpretation of this, think about the population correlation, what it looks like. So this is basically like the numerator is like a sample covariance, and the denominator is like the sample variance of x times the sample variance of y. So this is sx squared, and then this is sy squared. And this is like the numerator is like the sample covariance. Okay, sorry about messing that up, but and this kind of makes a lot more intuitive sense. So beta hat 1 is rho hat times sy over sx, and beta hat 0 is just y bar minus beta hat 1 x bar. So this gives you a lot more kind of intuition as to what's going on. And then the other thing that's important about that is that so to calculate beta hat 0 and beta hat 1, you don't need to know all values xi, yi. So you don't need to know everything. You just need to know the summary statistics you need to know, obviously, x bar, y bar, sx squared, sy squared, and rho hat. And so you only need to know these 5 values, and then and so if you know that, then you can calculate beta hat 0 and beta hat 1. Because again, I'll just kind of remind you of these formulas that beta hat 0 equals Sy over Sx. And just to make sure that there's no confusion, I'm going to write out these definitions again. And I guess I'll just use the shorthand here of okay. So this is just the definitions of those 5 key statistics. Once you know those, you can calculate beta hat 0 and beta hat 1. The next thing I kind of just want to quickly point out is that so there's actually we haven't actually used the fact that the epsilon i's are normal or independent for that matter anywhere so far. All we've done is use the least squares estimator, and that has nothing to do with normality. But what we can actually show is that the least squares estimator for beta hat 0 and beta hat 1 is equivalent to the maximum likelihood estimators. I mean, we're not going to spend too much time on this. I just kind of wanted, this assumption of normality is going to really come in handy here when we start to talk about kind of distributions of these beta hat 0s and beta hat 1s and so on, which we'll get into a lot more in the next lecture. But one of the cool things about assuming that these epsilons are normal and independent is that we can say that the maximum if we would try to find the maximum likelihood estimate for beta 0 and beta 1, that's equivalent to the that's equivalent to the least squares estimate. So let's see why. So so to show this, another way to think about this is that yi is normally distributed with mean beta 0 plus beta 1 xi. So you can think about the regression line as really just being the mean of the mean of these yi's, and then with a variance of sigma squared. And so the distribution of yi, we'll say, given the xi's, because these xi's are kind of given to you, there's these 3 parameters here, and then you take this e to the power of squared over 2 sigma squared. And if you look at the likelihood of beta 0, beta 1, sigma squared, y xi, that's going to be the product of these things. So it's going to be the product of these PDFs, and so and then I'm going to write x here to be the exponential. So this is going to be Okay, and so maximize L of beta 0, beta 1, sigma squared, yi, xi. That's the equivalent. We're going to try to maximize these over beta 0, beta 1, and sigma squared. That's equivalent to minimizing over the negative log likelihood, as we've seen before. So negative log of and so this is just going to be n log sigma plus n over 2 log 2 pi, which we'll see doesn't matter too much, and then we're going to have plus 1 over 2 sigma squared. Okay. And so you can see that we want beta hat 0, beta hat 1, and then sigma hat squared is going to be the argmin of beta 0, beta 1, sigma of n log sigma. We can forget about the n log 2 pi because it doesn't contain any of the terms here. Okay. And so now if we, so we want to minimize over beta 0 and beta 1. And you can kind of see that that doesn't really depend on sigma because the sigma terms, like if you were to take derivatives, the sigma terms would go away. What you get is this. So this is just equivalent to argmin beta 0, beta 1. Okay, and this is exactly just our residual beta 0, beta 1. Okay, so if that last step's a little bit confusing of how you get rid of the sigma, just kind of go through the steps yourself of like taking derivatives with respect to sigma and beta 0 and beta 1, and you'll see that that you can kind of ignore those sigmas because once you take the derivative with respect to beta 0, that first sigma term goes away and the sigma squared here just becomes a constant. So that's why you can, the least squares solutions to beta 0 and beta 1 are equivalent to the maximum likelihood estimate. So this is kind of a cool thing that, the least squares is a very general way to find the regression line, and it doesn't make any assumptions about normality or anything like that. But under the model that we have normal and heteros and home, like normal errors with like independent normal errors with the same variance, you get that this is just the same as maximum likelihood. So I'll just write that down. So under independent homoscedastic just means that all of the noise is the same noise. So that just means that epsilon I is normal 0 sigma squared independent. Minimizing distance or least squares, and maximum likelihood estimation are equivalent. Okay, and so we've talked about estimation of beta 0 and beta 1. So what we'll finish with today and in the next, and this will set up the next lecture where we start to talk about confidence intervals and finding and hypothesis testing as well. So the one thing we haven't talked about is estimation of sigma squared, and This is actually very related to what we learned about in ANOVA, like how do you estimate sigma squared. So recall that for two-way, for ANOVA, and this is something that's very common throughout, is that sigma hat squared is like the, I guess you could say SS error divided by the degrees of freedom. And a very similar principle. So SS error is equal to something like, the summation I, summation j of like yij minus, y hat ij squared, where this is like the fitted model. Remember, there were 3 different ANOVA models that we had. We had like, for example, you could have that y hat ij is equal to like alpha hat I plus mu hat. That was one example that we had, where, like for one-way ANOVA. For two-way, we had y hat ij, like alpha hat I plus beta hat j plus mu hat, and then we had another example when we had two-way ANOVA as well. But essentially, the idea in regression works very similarly. So for linear regression, we're going to let this is called the residual sum of squares. So residual sum of squares is just equal to R of beta hat 0, beta hat 1. And so that just equals to yi minus beta hat 0 xi squared. Okay, so this obviously depends on your estimates for beta hat 0 and beta hat 1. And so what this is that you can say that sigma hat squared as an estimate is just RSS over n minus 2. So this is like the degrees of freedom. This is the degrees of freedom for the residuals. So that's just equal to okay, and so where does n minus 2 come from? So you're hopefully starting to get the hang of this. So it comes about because we have n data points, but then we 2 parameters. So you'd start with kind of n degrees of freedom, but we lose 2 because we estimate beta 0 and beta 1. So that's, remember that I mentioned that one way to interpret degrees of freedom is the number of samples you have minus the number of samples you have minus the number of parameters that you're trying to estimate, because in some sense you have to use the data to estimate each of the parameters that you have. And so this is our estimate for sigma hat squared that we typically use. Another way that you can kind of try to think about this or figure it out yourself, which is something we did for one-way ANOVA, is that if you look at this expansion. If you looked at, yi, if you wanted to expand out, I'm stuck here. If you look at, you can kind of write out this expansion as okay, and so you know, this is approximately, and I'm not going to be too exact because I'm a little bit imprecise here. This is just equal to beta 0 minus beta hat 0 squared. I'm or a better way to say this is that you can kind of show that this thing plus the beta hat 0 squared plus xi, this whole thing squared. This is approximately, you know, the sum of y equals 1 to n yi squared. And so this is, you get kind of n degrees of freedom here, 1 here, and 1 here, and then this gives you n minus 2. But again, I've been a bit imprecise there. If you want more details on that, then yeah, I would encourage you to look in the textbook, because there they kind of do this this expansion more. The main thing I'm trying to do here is just to give some intuition as to why we have n minus 2 degrees of freedom there. So far, we have estimators for beta hat 0, beta hat 1, and sigma hat squared, based on and that's based on x bar, y bar, sx squared, sy squared, and rho hat. So the next question is, you know, to find confidence intervals and do hypothesis tests. So, you know, what is distribution of beta hat 0, beta hat 1, and sigma hat squared? Okay, so that's the question that we're going to mainly tackle in the next lecture, but just to get you started. So, you know, for beta hat 0, we have that beta hat 0 is and beta hat 1 is equal to x bar, and then we also know that y bar is going to be normally distributed with mean of beta 1 x bar, and then this is going to be sigma squared divided by n, because we're taking a mean. And then we also have that yi beta 0 plus beta 1 xi sigma squared. And so we're going to use these facts to actually come up with our distributions for our beta hat 0 and beta hat 1. So therefore we can say that beta hat 0, beta hat 1 have normal distributions because they're just linear combinations. We just need to find the variance of beta hat 0 and the variance of beta hat 1. Okay, so that's something that we'll do because we've already found their means here. And so we know that beta hat 0 is normally distributed with a mean of beta 0, and then I guess we'll just say variance of beta hat 0, and then beta hat 1 is normally distributed with a mean of beta hat 1 because we've already calculated that, and then the variance of beta hat 1. Okay, and so we need to just find these, and that's what we'll do in the next lecture. So and in addition to that, we'll also look at the distribution of sigma hat squared, which we can potentially guess is going to be related to the chi-squared distribution. Okay, thanks very much. That's it for today. And so there's just one more lecture to go in terms of new material. Okay, thank you. Bye.